So, as a final example of divide and conquer, we will look at a problem called quick select. So, selection is the problem of finding a specific position in a list. So, in particular we want to find the kth largest value in a sequence of length n. So, of course, one way to do this is to sort the list in descending order, and then the largest value is the first one, the second largest value is the second one, and so on. So, by just looking at position k in this sorted list in descending order, we will get the kth largest value. So, since we know we can sort in n log n, this would mean that the kth largest value, the selection problem of finding the kth largest value also takes n log n. But if we look at some special cases, it perhaps suggests that we could do better. For instance, if we want k equal to 1, then we are just looking for the largest value in the list, and that is just the maximum, and we know that we can compute the maximum in a list in a single scan. So, it only takes order n time, it does not take n log n time. Similarly, if k is equal to n, that is we want the smallest value in the list, then we can just compute the minimum in a single scan of order n. So, the question is, can we do this for all k? So, if we fix a k, then of course in the first pass we can find the largest, and then among the remaining in the second pass we can find the second largest. So, we can make k passes, and in order k times n time we can always find the kth largest. Now, the problem is that as k becomes large, in particular if k is like n minus 1 or n by 2 for instance, then this will become order n squared, right. So, in particular the median is the value in the center of the list. So, if we sort the list, then the median will be the value at position n by 2. So, if we just use this naive thing here, then the time it will take to find the median is n by 2 passes on a list of length n, which will be order n squared. Now, remember that one thing we had said before is that if we can actually find the median quickly in order n time, then what we can do is we can take this list and then find the median as the pivot, and then create this lower list and this upper list, which are roughly half, because the median will divide it into two parts which are half. And if the two are half and we recursively sort them, then we will get a recurrence like merge sort. So, quick sort will also become order n log n. So, that would be a side benefit of being able to do the selection problem in order n time. So, first let us look at a divide and conquer solution which is similar to quick sort. So, remember that in quick sort we used a pivot to partition the sequence that is given to us into two sequences, the lower part, everything that is smaller than or equal to the pivot, and the upper part, everything which is bigger than the pivot. So, now we have this lower part. So, remember the way that quick sort partitions is to put the pivot in the middle and put the lower part before and the upper part after, and we know that everything in the lower part is smaller than or equal to p, and everything in the upper part, say, is bigger than p. So, now we are looking for the kth largest element. So, the point is that if this particular segment, right, if this segment is less than equal to k, then the kth largest element actually sits in the lower part. So, we can look at the length of the lower part and determine which of these three segments we are going to find the position that we want. Right. So, if k is, so let m be the length, right. So, m is the length of this lower segment. So, this is m. So, if k is less than or equal to m, then the kth largest element of the whole sequence actually lives in the lower part. So, we can search there. If k is equal to m plus 1, then this must be the value that we want. So, we can return the pivot. And if k is greater than m plus 1, then we know the answer lies in this part, right. So, this now gives us a recursive strategy. So, the recursive strategy is that if k is smaller than or equal to m, we just apply this selection procedure to just the lower part of our sequence and look for the kth element there. If it is m plus 1, then we just return the pivot, we do not have to do any more work, we have found the element that we want. And finally, if it is bigger than m plus 1, we must select the upper one, but now we must change the value we are looking for, because we have this lower set, right. So, this is m and we have this one element which is the p. So, we have to subtract. So, now we are looking for the kth element overall, but we are looking from here onwards, we want a value which is k minus m plus 1, right. So, we must change the position that we are looking for from k to k minus m plus 1, because we are now looking beyond the pivot. So, this becomes now a recursive way to divide and conquer and compute the selected value that we want. So this is something which, since it is derived from quicksort, let us call it quick select. So very similar to quicksort, we can write this quick select. So quicksort had a list and it had a lower and upper bound L and R, but we also now add a fourth parameter k, which is the position that we are looking for, right. So we are trying to find the kth largest parameter in the slice of this list from L up to R minus 1. So the first thing is that this k is kind of absurd, then we will just quit. So if k is smaller than 1, so our values are from first largest, that is 1th largest to nth largest. So if it is less than 1, if I ask you for the 0th largest thing, then you will just return none. Similarly, if the k is larger than the number of elements in my list, right. So R minus L is going to be the number of elements in my list. So if either of these two cases are there, then I will just return none as a kind of answer saying that this query is not valid. Otherwise, we do exactly the same partitioning as we did for quicksort, right. So we set the leftmost value in our slice to be the pivot, and then we maintain these two pointers. If you remember, we maintain these two pointers, and then we slowly scan from left to right and gradually partition this into lower and upper, right. So that's what happens here in this loop, right. And then once we have got that, then we want to exchange the pivot with the last position in lower, and that's what happens here. So this is exactly the same partitioning strategy as quicksort, nothing new here. Now, unlike quicksort, where we are going to examine both halves and sort them recursively, here we are going to do this check, right. So the first thing is we compute the length of the lower segment. So the length of the lower segment is the position lower is actually the first index outside that, right. So it's like saying that if it is n, then it's n minus 1. So the lower length is the value lower, which is the position marking the end of that segment, minus 1. So now if the position k that we are looking for is less than or equal to the lower length, then we will recursively quick select on the lower part, right. So I will go from the left limit L to the upper limit lower and look for the kth element. So that's this case, right. Otherwise, in the second case, if the k I am looking for is exactly equal to the length of the lower half plus 1, then I will directly return the pivot, which is just the value at the position index lower. And finally, if it is not either of these two, then I will run quick select on the right half from lower plus 1 to R, but I have to change the index from k to k minus m plus 1, where m is now for me this lower length. So what we have done is we have basically taken quicksort and we have taken the partition algorithm exactly as in quicksort, and then after partitioning, instead of sorting the two halves, we are suitably choosing which part of the partition to select. So either we select in the lower part or in the upper part, or we just directly return the pivot. So if you want to analyze this, then the recurrence is very similar to quicksort, right. The only difference is we are not going to look at both halves. So we are going to look at, let m be the length of the lower part. So we are either going to look at the lower part or we are going to look at the upper part, and in the worst case we have to go with a larger one. So instead of saying T of m plus T of n minus m plus 1, which is what we would do if we had quicksort, because we would have to solve both problems, here we are going to do the maximum, one of the two, either the left half or the right half, and in the worst case it will be the worst one of the two, so it will be the maximum. Plus of course there is this order n work, which is the partitioning part, right. So I have to go across this entire sequence in order to partition it. So there is order n work to partition, even though after partitioning I don't have to do any work to recombine, unlike in merge sort. So of course we know what happens, which is that when our pivot is an extreme value, then either I will have an empty lower part or an empty upper part. So m will be either 0 or n minus 1, and I can engineer it so that it happens with every recursive call. So every recursive call, this maximum might well be where m is 0, for example, it will be t of n minus 1, right. So in the worst case, this quick select will also have a recurrence which says t of n is t of n minus 1 plus n, just like the worst case for quicksort, even though we are not doing both halves, we are doing only one half. And in quicksort, the other half disappears because if in the worst case, sorting the empty half is trivial. Whereas here we are only looking at one half, and that one half is a big half. So quick select is again n squared, right? So this divide and conquer has only got us our n squared thing, and we know how to do n squared by brute force, right? We can do n squared by just doing one scan for the first element, another scan for the second largest element, another scan for the third largest element. So it appears that this quick select, even though it is a clever way to do this, is not really any better than the brute force way of doing n nested loops. But last time when we had looked at this recurrence tree analysis, what we had said was that if you can somehow find a pivot which is not necessarily the median, but it is some fixed fraction away from the thing. So for instance, if it is between 1/3 and 2/3, right? So if you arrange the values, if your pivot is guaranteed to be in the middle third, so supposing my values are arranged in ascending order, I am not promising you the pivot is in the middle, but I am saying that the pivot is going to be somewhere in this segment between 1/3 and 2/3. And it can be 1/3, 2/3, can be any fraction, it could be 1/5 and 2/5. This is also fine for or 4/5, sorry. So for any fixed, if I can knock off a fixed fraction by choosing a good pivot, right, then the claim is that quicksort will actually become n log n. So last time we saw for this 1/3, 2/3, right. So supposing the pivot lies between the maximum value by 3 and the maximum value times 2 by 3, right. So if this is the case, then the recurrence we get is that we are guaranteed that the smaller of the two partitions is at least 1/3 in size, because the pivot is no more than 1/3 away, I mean at least 1/3 away from the boundaries. So we have the smaller of the two partitions is n by 3. So the worst case is one is n by 3, the other is 2n by 3, and if we solve this, then we get n log n. So the question is whether we can somehow manufacture this for our case, right? So can we find a good pivot of this form, a pivot which is somewhat guaranteed to give us a fixed fraction of elements that will be pushed into one of the two partitions, rather than this extreme case of 0 which we have when we take just the position at the 0th, the value at the first position or the last position in the list, or any fixed position. So here is a very clever idea which achieves this. So this is called the median of medians. So what we will do is we will divide L into blocks of 5. So we will take our list, right, and then we will write the first 5 elements and then the next 5 elements. So we will just block it off into blocks of 5, right. So we will take the first block of 5 elements, the second block of 5 elements, and so on. Now for each block of 5 elements, we can find the median by, if necessary, by brute force. We can sort it and find the middle one, or we can just rearrange it by any standard sorting algorithm and find the value in the middle, right. So for a block of 5 elements, it's a constant amount of work, because the block size is fixed to be 5. It's a constant amount of work to find the median of that block. So we can find the median of the first block, we can find the median of the second block, and so on. So we can find the median of each block. Now of course it could be that the final block has not got 5 if it's not a multiple of 5, but as usual we will assume that it's always going to be some kind of power of 5 for the analysis to be simple. So in this way we have now taken this and we have picked out one element from the first 5, the median, one element from the second 5. So each block we have got the median, right. So now we collect these medians. Right. So we collect the medians. So we have, just to remember, so we have some x1 to x5, and then we have some y1 to y5, and then we have some z1 to z5, and so on. So from here I will get some value a1, that is the median of this thing. Then from here I will get a value b1, which is the median of this thing. From here I will get a value c1, which is the median. So I will collect one value, namely the median, from every block, and I will create a new list, and this new list has the size 1/5 of the original list, because I am only picking 1 in 5 from every block. And now what do I do? Well, I will recursively do the same thing for this list M. So I will again divide this list of block medians into groups of 5, and again find the median of each of those blocks and pull it out, right. So that's why this is called the median of medians, right. So I find blocks, I take the median of each block, I collect it into a list, I make blocks, I collect it into a list, I keep going until when? Well, until the blocks that I have collected amount to 5 or less, and then I just take the median at the end. So that is my base case, right. So here is the algorithm in Python, right. So I take a list and I want to compute this median of block medians, right. So if the list is smaller than 5, then I will just do some brute force. I will just sort it and return the middle element. So I just take the length of the list and divide by 2, and that should be roughly the middle element, right? It might be plus minus 1, it does not really matter. Otherwise, if it is bigger than 5, I will do this grouping into 5s, right? So I will start, so capital M is going to be my collection of medians. So initially I have no medians to collect. Now what I will do is I will look at indices 0 to 4, then 5 to 9 and so on, right? So I will say let I be 0, then let I be 5, then let I be 10. So I will take the range 0 to length of L in steps of 5, right? And now I will take the slice from I to I plus 5. So this is 5 elements, I plus 1, I plus 2, I plus 3, I plus 4, right? So I take those 5 elements and store it into a new list. I sort that list exactly as I did in base case, right? And I take the median of that list and append it to this collection of medians that I am going, right? So I am just taking the first 5, finding the median, putting it in. Now one thing to note is that if I know that there are 5 elements, then the median is always x2, right? Because x0, x1, x2, x3, x4. So after I sort it, I know that the second position, the position index 2 is the median. But the problem is that I might have at the end an odd block which is not 5. So if I have an odd block which is not 5, supposing it has only 2 elements, then if I ask for position 2 in a 2 element list, it will be outside and I will get an index error. So it's always safer to just say that take for each block that I construct, which is typically 5, but the last block may be smaller than 5, sort it and take the middle position by taking the length of that block divided by 2, right? So what we have done is basically we are sequentially going block by block. We take the first 5 elements, put it in X, compute this, sort it, take the middle element and put it out into M, take the next block and so on, right? And now having constructed this M, we just recursively call our function on this list, right? So this will again divide by 5 and do it and keep doing it until the shrinking by 5 brings us to a list which is smaller than 5, and then the base case will exit. So this is our median of median algorithms. So the goal of doing this was to guarantee somehow that the value that we pick out of this, so you can check that this is not going to be the actual median, but we don't want the actual median. What we want is a pivot value which is guaranteed to give us some fixed fraction of elements in each of the partitions. That's all we need in order for our quick select or quick sort recursion to give us an n log n or order n thing. So let's see why the median of medians that we are constructing is a good value. So if we visualize the blocks, right, so this is my block 1. So these are my first 5 elements. So each column in this is, so this is my entire, from left to right is my entire list, and I have been grouping it in groups of 5. Now of course each of these 5 is not sorted, but let's pretend that it is sorted, right? So let's visualize it so that each of these blocks of 5 is internally sorted like we did here, right? So we are looking at this value, this x after it is sorted. So we keep this, so we are not actually doing this in the original list, we are just doing it block by block, but let's imagine that we actually collected all these sorted blocks. Then where would the median of each block lie? It would lie in the middle of that thing, right? So these yellow things are the medians of each of the blocks, right? And now the yellow things are going to be finally passed back to the median algorithm. So we are going to get this blue thing which is roughly the middle of that sequence as our final median of medians. So the question is, what can we say about how many elements are below or above that blue one, right? So this is our question. So if you think about it, okay, everything which is to the left of this, all these are our old medians, these are all smaller than the blue ones. And within each of those blocks, everything which is above is also smaller, right? So all these positions which are marked in this brown color are smaller than our median of medians. And symmetrically, if you drew it here, right, everything in this section would be larger than our median of medians, right? So you can see why, because everything in this row, the same row as the median, is a block median which is smaller. This is the median of the block medians. So this row is all the block medians, and these are all smaller than the blue element, and within their corresponding blocks there are 2 elements smaller than each of them because they are the medians of their respective blocks. So how many brown elements are there, right? How many brown elements are there? Well, this is roughly half, right? So if I had length of L, right, So this is roughly half on the left of the blue elements, and within that I am taking 3 by 5. Out of every 5 I am taking 3, so I am taking 3 by 5, right. So this, the number of things in the brown thing should be 3 by 5 times the length of L by 2, so that is 3 by 10 times the length of L, right. So this is going to be the smaller part of the thing, so at least 3 by 10 of the elements are smaller than this median, and at least 3 by 10 are larger than the median, right. So that's going to say that the median lies between these values, right. So if you take the maximum value and I take the things, is going to be between 3/10, so I'm going to knock off at least 3/10, this is what it means. So now this gives us a strategy to get this block of medians, right. So let me change that quick select and call it now fast select, right. So fast select is like quick select, except that instead of picking the first position as the pivot, it calls this median of medians, right. So you want to find the quick select the kth element in capital L from the slice L to R, right. Instead of taking the position L as your pivot, you call this median of medians algorithm on this slice. Now of course this will give you a pivot somewhere in this slice, so you have to find that position. So we will find the first I in this range which has the value of the pivot, right. And then we will, just to make the rest of the partitioning look similar, we will move that pivot to the left hand side, right. So what we are saying is that you give me the slice L from L to R, right. I run median of medians on this and I will get a pivot, and I will now take this pivot and move it to the beginning so that the rest of it can run as before, right. So I move this pivot from wherever it is as found by the median of medians thing to the left hand side, and then I run everything as before. The partitioning is as before, right, and the recursive calls are as before, except that instead of calling quick select, of course I am calling fast select. So the only thing I have done is I have changed the way I compute the pivot. Instead of taking the leftmost element, I am using this median of medians and then doing it, right. So first of all, how much time does it take to run median of medians? Well, that is easy, right. Median of medians is basically taking the entire thing, doing a linear scan. So in order n time, it's reducing the problem to 1/5, and then it's again reducing the problem to 1/5, right. So this is one of our contracting series, and so this whole thing is going to be dominated by the time it takes at the root, as we saw. So it's going to be order n. So the median of median finding this is actually order n time. So finding the pivot is order n time, and finding the partition is also order n time because I do it in one scan. So overall, as far as this fast select is concerned, right, this part of it remains order n. The processing time at each recursive call without the recursive call being counted is order n. It's order n to find the median of block medians, and another order n to do the partitioning with respect to that median, right. And now what do we know? We know that, like our earlier example of quicksort with 2 by 3 and 1 by 3, here we know it is 3 by 10 and 7 by 10, right. We know that at least that many elements have been eliminated in this or pushed into one of the two partitions, right. And since we have this, it is similar to our earlier thing that we will just keep contracting, right. The maximum of this is strictly smaller. So basically this recurrence of fast select is going to be dominated by what happens at the root, and I am going to get that fast select also runs in linear time, right. So this is it should be big O of n, right. So Tn is also big O of n, right. So we have moved from an n squared algorithm to a big O of n algorithm by using this very clever median of medians argument in order to find a pivot which is in a range which is guaranteed to be between 3/10 and 7/10 of the positions in the array, right. So we can of course use the same trick in quicksort, right. So in quicksort also we can, instead of taking the extreme element or some fixed element as a pivot, we could call median of medians. In order n time we will get a good pivot. We will reduce quicksort to taking quicksorting 3 by 10 and 7 by 10, and it will become n log n. Now of course there is a cost involved with this, so there are some constants and all that. So when I say that this is going to be order n, it's going to take some extra cost compared to just doing a partitioning, and we can basically see that in quicksort on an average it will be n log n even without doing this work. So we typically do not use this because this overhead actually makes quicksort slower in the long run, because in the cases where it would run in n log n anyway, by adding this overhead of medians, we are actually doing extra work. But it's useful to know that quicksort can actually be made to run in n log n time in the worst case by applying this median of medians as our pivot strategy. Right. So to summarize, the median of block medians will help us to find a good pivot in linear time. And now if we use this as our strategy to choose the pivot for our partitioning, then this quick select actually becomes a linear time algorithm, and quick sort becomes an n log n algorithm in the worst case with this extra step. This also means that we can find the actual median in linear time, because in particular this finds the kth largest number for any k in linear time, and if I say k is n by 2, right, then I can actually find the middle element in the sorted sequence in linear time. So I can actually find the real median. So even though the median of block medians is not the real median, it's somewhere between 3/10 and 7/10, right, but still I will also be able to find the exact median by using quick select with median of medians. So you can actually work it out that you can actually build in that median of medians and make it a single algorithm which will find it, but it's more transparent to keep it as two separate things. There's a median of block medians and then a quick select. So you apply quick select with k equal to n by 2 and call median of medians for the pivot, and you will get the actual median in linear time. So historically, of course, quicksort is very closely related to quick select, and in fact Tony Hoare, who invented quicksort, also described quick select in the same paper. So in 1962, the paper that talks about quicksort also talks about how you can use it for selection. So quick select was already known, and this clever algorithm, which is there for median of medians, came up over 10 years later in 1973, and this is again a bunch of heavyweights in computer science. So Manuel Blum, Robert Floyd, Vaughn Pratt, Rivest and Robert Tarjan. So each one of them on their own has made seminal contributions to various aspects of computer science, and together the five of them came up with this very clever idea of median of medians, which makes both quick select and quick sort much faster.